Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of used cars, and we're going to try to predict the price of a given car based on a series of attributes. Alright, so I'll get right into it. We have the task for today, given data about used cars. Let's try to predict the price of a given car. We will use linear regression and gradient boosting to make our predictions. So, I'm starting by importing NumPy and pandas, and train test split and standard scalar from sklearn for pre-processing. For our actual models, we're going to be using linear regression and lightGBM, which is a gradient boosting library, and we will use this metric, mean squared error, from sklearn. Alright, so I'll import that, and I'll load in our data using pandas.readcsv. And I can get the file path right over here, vehicles.csv, paste that in, and we'll take a look. And let's see, it has 423,000 rows, but it shouldn't be taking too long. Alright, it's in. Here we have. So right away I notice that we are not seeing all of the columns. And immediately I'm going to go into the terminal and write pandas.set option max columns none. And when we reload this, now we can see them all. And we have 25 different features, or different columns. And we can see that there's some substantial amount of null values in here. Maybe not. There's 420,000 rows, so maybe these are the only nulls in the whole data set. I think that's the first thing we should check, though, is figuring out which columns have too many null values. So let's do data.info to get a little preliminary information on it. And the first thing that strikes me is that this has 0 non-nulls, which means the entire column is useless, full of null values all the way. And we have some large number of null values in some of these other columns. So I guess we can start pre-processing. So let's look at the null count in each column. So we're summing across the is and a's, which will give us the number of nulls in each column. And it looks like, luckily, what we're trying to predict has no nulls. So that's good. Additionally, state has no nulls, and these ones have no nulls. But these three actually, ID, URL, and region URL, are probably not going to be very useful to us. So let's see. Another thing we can do, instead of summing over the nulls, is taking the mean. And what that'll do is give us the percentage of null values in each column. So this one has 100%, as we saw earlier. Right here, county has 100% null values, and a lot of these have upwards of 50% as well. So what I like to do is I'm going to drop any columns that have over 25% null, and this could be chosen at random, really, or however you like. But basically, if this is over 0.25, we'll get trues every time it's over 0.25. And then what we can do is index data.columns at these truth values to get only the column names that have more than 25% null values. So we'll call that null columns. And we're going to drop those null columns from the dataset. So axis 1, data equals that. Alright, so now let's take another look. we have 15 columns now, so we've dropped like 10 columns. And we want to see, okay, which of these columns do we not need? I'm going to call this unneeded columns. So the reason what I mean by not need is which of these are not going to give us any useful information for predicting the price. So ID obviously is not going to give us any information. URL and region URL as well. These two are fine, model's fine, this is all good. Image URL not going to give us. Although theoretically we could use the image URL to load the image and use the actual image data in a convolutional network to give us some more useful information, which may actually prove to be promising, but for the purposes of our video we're not going to do that because that would take a lot of time. I don't want to keep it simple. Description we don't need either because it's not clear how we would process description. Although we could probably find some creative ways to do it if we really wanted to. Alright, so we're going to drop those. And now let's take one more look. We now have a nice sort of smaller, cleaner data set, still with a large number of rows. So now what we should probably do is deal with the missing values. Right? However, I noticed that a lot of these columns have categorical data. And with categorical data, I can't just fill in the missing values based on the mean or some other value. So normally I would impute the missing values of like for example, if latitude is missing a value, I can fill it in with the mean of the column. And I can do that for any numerical column. But I can't do that for these. So what I'm going to do is get an idea of like how many, because I want to deal with the categorical ones first. Because when I one-hot encode the categorical columns, that will take care of the null values right away. It'll just encode all zeros wherever there's a null value. All zeros in the dummy columns, I mean. So let's see. I want to get an idea of like how many unique values are in each of these categoricals. Because I have to know based on that, like how am I going to encode these, and also are there any that I don't want to encode because there's just too many unique values. If we have too many unique values in a column, it's usually not worth it to one-hot encode because it can severely decrease the performance of the model if there's just way too many columns. So what I'll do is I'll make a dictionary that's going to take a column name and map it to well, we could say the unique values of the column, but I actually want to get the length of that. So I want to know how many unique values are in each column. And that's for every column in data.columns if data.dtype subcolumn equals object. So meaning only categorical columns. And we can see, so region has 404 unique values. That's pretty decent. We can still one-hot encode with 404. But model has 27,000. And I'm not going to add 27,000 columns to my data set because it will really increase training time, and I'm not sure if it's really going to give us so much useful information. Although I certainly could. There's no reason that I wouldn't be able to. But we're going to keep fuel, we're going to keep title status, we're going to keep all these. Okay, so we're just going to drop model, data.drop model. And I realize that we may be dropping useful information here, but for the purposes of the video, I'm trying to keep it simple. So there we go. And now for the other ones, we're going to one-hot encode. So I'm going to write a function, one-hot encode. That's going to take in a data frame some list of columns, and some list of prefixes. And we're going to start by making a copy of the data frame. And then we're going to construct, actually I'm going to do a for loop for every column prefix pair in the zipped columns and prefixes. So zipping them will pair them element-wise into tuples, so I can index them one at a time. And we'll create the dummies data frame using pandas.getDummies. And I'm getting the dummies for a specified column, and the prefix is going to be the prefix of that given column. Since they're zipped, they'll go together, so column and prefix will always be paired together. Then I will concatenate the original data frame and the dummies data frame along the column axis, and then I will drop the original column. Then I'll return the data frame. And that's our function. That will one-hot encode a data frame given a list of columns to encode and a list of prefixes to append onto the dummy columns for a given column. So I'll just say data equals one-hot encode data, and the columns we want to encode are these, except without model. So region, fuel, title, status, transmission, and state. And then I'm going to include the prefixes for each one. So we can say reg for region, fuel is fine for fuel, title for title status, trans for transmission, state for state. And run that, take a look at data when it's done. And what we should have is now a lot more columns, 473. When we have all these one-hot encoded columns for each of the original categorical features. But with that, we now have all numerical data. And so now we can mean impute for these ones, because these probably still have some nulls. Now we don't have to worry about categoricals. So I can actually just say for data dot, for column in data dot columns, data subcolumn equals data subcolumn dot fill NA with data subcolumn dot mean. So we're filling each column with the mean of that column and setting the new column to be that value. Alright, we'll run that, and now if we look at the isNA.sum, so I'm summing across the rows and columns to get the total number of nulls, we should get 0. We have no more null values, and we have fully numerical data. So, with that, we are ready for splitting and scaling. So we're going to split our data into x and y. Y will be what we're trying to predict, which is just the price column. So data.loc, all rows, just price for the column. And x is going to be everything except the price column. So we're dropping price from axis 1. Then we're going to create a scalar object. This I imported from sklearn. Standard scalar, which will give every column mean 0 and variance 1. And x is going to be scalar.fit transform x. Okay, now x should be, when that's done, you'll see it's going to be all values close to 0. And sure enough. Okay, so now, since all of our columns take on similar range of values, we should be ready to create a train and test split. So xtrain, xtest, just going to split the x's into 2 sets, and we're going to do the same thing for ytrain, ytest, using the train test split function from sklearn. We'll give a train size of 70%. And since it shuffles the data and takes the train size randomly, takes the train set randomly, we're going to include a random state so we can reproduce the results. And we'll do, how about 34? Alright. And then So we're ready to train, actually. Alright, so what I'm going to do is first I'm going to start off with a linear regression model, and we're going to see how it performs. It's probably going to do very poorly, especially because this was, you know, first of all, used car prices in the first place are not very easy to predict in general, because the prices are all over the place. But additionally, the data set is not very clean, and we had to drop a lot of information from our original data. So I'm guessing we won't get very good results from this. But I'm pretty much doing this to demonstrate how gradient boosting can significantly improve the results. So we're going to start with a linear regression model. I'll call it lin model. That'll be linear regression from sklearn. And lin model.fit. I wrote line, hold on. So we're fitting on the train set, xtrain, ytrain. And then I'm going to store the predictions, so lin ypreds in lin model.predict xtest. So we're going to make predictions on the test set after we've trained. And I'll run that. And then I'm going to do the same thing, but using the light gradient boosting model, so LGB model. So this is using, so I imported at the top, light GBM. So it stands for light gradient boosting machine, and it basically is a library that has a series of different gradient boosting methods that we can use to try to improve the performance of our regressor. So LGB regressor is the name of the model. Is it LGBM actually? Yeah, LGBM regressor. And so this takes in a few things. First, a boosting type. We're just going to use the default, which is a gradient boosting decision tree model. So GBDT, and we will include the number of num leaves for a given tree, and we'll just leave the default at 31, and then also the number of estimators to use, and the default's 100. We can leave it at that. I'll also include a bit of regularization on this. 1.0 sounds good, and that's L2 regularization. Then when we're done, we can fit that model on the train set as well, and create some predictions this on the test set, the same way we did for the linear one. And oh, what happened? I should actually say, oh right, actually, this should be LGB dot LGBM regressor. Alright, and that will take just a little longer to train. So in the meantime, I'm going to construct the losses. So we're just going to get the losses for each one. I want to get the RMSE, or root mean squared error, which will be the square root of the mean squared error, which I imported from sklearn.metrics, of the true y values and the predicted y values for our linear model. So lin ypreds is what we called it. And then I'm going to do the same thing, but for the LGB model. So grab this and this. Okay, we'll get those. And now let's print out, we're going to print out the RMSE and the R squared values for each model, just to compare the results. So we'll start with the linear regression RMSE, and we'll get lin loss from that, and then we'll do the same thing. This will be the LGB loss, and we'll say gradient boosted RMSE. Alright, and you can see right away that our gradient boosted RMSE is far, far better than linear regression. We got, this is 18 digits long, how huge that is. This one has only a loss of 4 million. So, it looks like, based on the other notebooks, some people were able to get it down to 300,000 or so, using gradient boosting. So I'm sure you could make further improvements on this. But I also want to show the difference in r² values. So linear regression r² score will be this. I'll just use linModel.score, and we're going to score it on x-test, y-test. And we'll do the same thing, but use the LGB model here. And this will be gradient boosted r² score. Alright, yeah, and you can see that this is much worse. Right, so neither one is very good. We still have negative values on both, but this is performing. Oh wow, I didn't even see this. Oh, much better. This is yeah, 23 decimal places long, and this one is very close to 0. So it's very clear that gradient boosting is doing a substantial performance increase here. So yeah, I guess that sums up today's video. Thank you so much for watching. If you enjoyed it, make sure to subscribe and leave any comments in the section below. And I'll see you guys tomorrow. Have a fantastic day.